In this lesson, we're going to continue talking about confidence intervals, but this time we're going to talk about it as it relates to mean. So we're going to estimate the mean of the population using a confidence interval. Now, there's a little bit of change that we're going to need to make between what we saw with proportion and what we're going to do with mean. And the big change is that we're going to use a different type of distribution. We used a normal distribution with z-scores for proportion. We're going to have to change that up to something called a t-distribution. So in practice, we really wouldn't know the population standard deviation if we're trying to estimate the mean of the population. So it really wouldn't make sense to know the population standard deviation if you don't know the mean of the population. And so when they did this, they just said, okay, well, we'll just use the sample standard deviation as an estimate for the population standard deviation. And they proceeded to do their calculations for confidence intervals using z-scores to do so. But that was okay when the sample size was big, but when the sample size was small, this started to cause some inaccuracies in your confidence interval. It wasn't fitting the probabilities that we were assuming were true. So then William Gossett from the Guinness Brewery, believe it or not, in Dublin, realized this problem when he was doing some experiments with hops and barley. And he was looking at small sample sizes. And he was just replacing the standard deviation of population with the standard deviation of the sample. And he didn't get accurate results. So what that led him to discover was that there's something called a student t distribution that we can use. And the student t distribution is basically similar to a normal distribution, and as the sample size increases, gets closer to a normal distribution, but isn't quite the same. So we're going to need to use a new set of values and really look at a new table. Instead of our normal distribution table, we're going to have a t-distribution table. But generally, the whole process will work out very similarly to what we've been seeing. So that's a little history behind it. So again, up until the mid-1970s, most statisticians did use a normal distribution to do what we're going to do here. But they realized that it really wasn't accurate when our sample sizes were small. And especially when sample sizes were under 30, it was really, really inaccurate. So we're going to switch to learning about a student t-distribution when we don't know the standard deviation of the population, which really wouldn't be realistic. Some times when you would learn this, certain textbooks teach it in two ways. We're just going to do it with the student t-distribution. So this is a formula for a t-distribution. And instead of a z-score, we have what we call a t-score. And this will work for any sample size n. So this is the formula that we will have for a student t-distribution. Some basic properties of a student t-distribution. The graph of a student t-distribution is similar to the standard normal curve in that it has a bell shape, but it has a slightly different curvature to it. And we'll see that when I compare them, and I'll show you pictures. The mean of the student t-distribution is 0, and it's symmetric about the mean, so that's very similar to the normal distribution. The mean sits in the middle and the mean is 0. So just like a standard normal distribution. The student t-distribution has more probability in its tails than the normal distribution does, just because the spread of the curve is slightly different. So let's compare the curves now. Rather than just stating the differences and similarities, let's look at them. So here you see there are 3 curves here in this picture. The blue, the red, and the green. Now the green curve is the bell that represents a standard normal distribution. The red and the blue represent 2 different t distributions. Okay? One where the sample size is 3, one where the sample size is 12. So notice, as the sample size increases from 3 to 12, the bell curve that is red, it gets very, very close to the bell curve that is green. So the student t distribution and the standard normal distribution start to become really, really close to each other. But when the sample size is 3 and it's very small, you can see there's a discernible difference. Again, they're all bells, but they're slightly different curved bells, okay? Which would then displace the area under the curve slightly differently. And so this is essentially the idea of a student t distribution. It's so similar to a normal distribution, but just a little off. And that being off by just a little bit could change the values in, say, your confidence interval. So that's why we're going to look at a student t distribution so we can get more accurate values. But just note that as the sample size, n represents the sample size, as the sample size gets bigger and bigger and bigger, this student t distribution starts to become more and more like the standard normal distribution. And that's why when we work with really large sample sizes, it's okay to just ignore student t and just do a normal distribution because the values will be so close to each other. But when your sample size is small, and generally if you're less than 30, there's enough of a difference that it's worth keeping into your student t distribution that we're going to need to learn how to do it this way. Couple of things we're going to need. We're going to need to talk about a critical value that's a t alpha half instead of a z alpha half. Degrees of freedom will also be something that's going to play a role in here. So let's start to think about this. So let's have a student t distribution. At first glance, it doesn't look much different than the pictures we were drawing previous to this, but this is now a t distribution. Okay? Then what we're going to do is we're going to look at our tails of the picture because of our confidence level. Same idea, right? We have our confidence level, let's say 95% confidence or 99% confidence. And the t-scores here, now remember, these are t-scores, not z-scores, because it's a t distribution. The t-scores, this would be your t alpha half that we would need to find. So this would be our critical value for the t distribution instead of the critical value for the z distribution. Very similar. How we find that is really dependent on two things. One, the confidence level, which we always put right here in the middle, right? That was our confidence level. And two, this idea of degrees of freedom. So degrees of freedom is an easy value to calculate. You do it n minus 1, n being the sample size. So it's always 1 less than the sample size. But you need both of those things to be able to find this t-score. And it's because we're going to be using a new table to do this. We're not using our z-score table anymore. We have a t-score table. So here's our t-score table. So let's just say we have a 95% confidence level. So similar picture I just drew. Put that right in the middle, just like we did before with z-scores. We want to figure out what this t alpha half is here. Well, what do we know? We know that the area in both of these tails combined is 5%. Or this one is 2.5%, and this one is 2.5%, okay? And let's just say we have a sample size of 15, because that's going to make a difference. Remember, the sample size changes the curve, which will change the disbursement of the area under the curve. And so if our sample size is 15, that means our degrees of freedom will be 14. It's always 1 less than the sample size. And so we look at this table. So this table is set up a little bit differently. Degrees of freedom are located here on the side, and our area in one tail or two tails is stacked up here on the top. Inside the table, these are your t-scores, okay? So again, that's a little different than the z-score table. So we have an area in one tail to be 2.5% or two tails to be 5%. Well, area in one tail or two tails, it's the same thing, right? So two tails with 5%, one tail is 2.5%. It still represents the same column. Okay, so it doesn't matter which one you use. The degrees of freedom is 15, which is here. So if I match, 14. So if I match those up and I look at it, that's going to be my t-score. That's my critical value t alpha half. So that's how we're going to find it. So you look at your confidence level, you draw your t distribution, look at your tails, how much area you have in either one or two tails. Doesn't really matter which one you look at. It will represent the same column. Go down your degrees of freedom to whichever your degrees of freedom are. Find your t-score in the middle. Done. Once we have that critical t-score, we have everything we need to get started here. Before we used proportion, we used the sample proportion to estimate the population proportion. Well, here we're going to just do that with mean. We're going to use the sample mean to estimate the population mean. So this is a starting point. Sample mean is a starting point for estimating it, but it's probably not completely accurate for the population mean. So what we're going to do is we're going to use an interval based off of our error and subtract it from the sample value and add it to the sample value, in this case the mean, to create our interval. It's the same thing we did with proportion. For proportion, we said the population proportion should be somewhere between the sample proportion minus E and the sample proportion plus E. We're just swapping out proportion for mean. The mean of the population uses the sample mean minus the error, the sample mean plus the error. Okay? So the interval is set up the same way. The difference here is that our error formula is going to be using t-scores. So we have t alpha half times s over the square root of n. And we saw that this piece with proportion represented essentially an estimate for the standard deviation, and we're basically using the same thing here. This is going to estimate our standard deviation for our population. So we plug all this stuff in. Standard deviation is the sample. We should be able to find that. Any sample we have, we should be able to calculate the standard deviation sample. This is sample size, and we just talked about how we get that critical t-score based off of our degrees of freedom and our confidence level. So here's a particular question that we can do. You do a study on hypnotherapy to determine how effective it is in increasing the number of hours of sleep subjects get each night. You measure the hours of sleep for 12 subjects. So there's your sample size. With the following results. These are the different number of hours that we got from our sample. Let's construct a 95% confidence interval for the mean number of hours slept by the population. Now, they gave you the data in this question. They did not tell you what the mean or the standard deviation from the sample is, but we learned how to do that in the beginning of the semester. So you're going to have to put a little work into this question to come up with the sample mean and the sample standard deviation. We know the sample size is 12. They also give us a confidence level of 95%. And from the sample size of 12, we know that degrees of freedom is 11. So we have generally a lot of the things we need, but in order to calculate the margin of error, we need our t alpha half, we need our s, and our square root of n. Well, we don't have t alpha half, we don't have s. We also don't have the sample mean as well. So we need to find all these things. Let's start with finding the sample mean. How do you find it? You should remember, you add all these numbers up and divide by the total number. So we'll add them up and divide by 12. So if we do this, we calculate the mean to be 8.98. Okay? Then we got to use our standard deviation formula, which takes a lot longer to do, but we know how to do that. We've learned that before. We would calculate the standard deviation. Good news is, for a lot of these problems that you'll have to do moving forward, they'll already give you the mean and the standard deviation from the sample, but we should be able to calculate both of them. So if we calculated the standard deviation, we would get 1.29. All right. So then we can go to our table and we can get our confidence level and our degrees of freedom to get our t alpha half. So we would draw our picture like this. We would say, okay, confidence level is 95%. Area in one tail is 2.5%. That'll be the middle column. Then we'll say our degrees of freedom is 11. Go down to 11, read it over, and our t alpha half will be 2.201. Okay? So now we have everything we need here. We have our means of finding the error, so 2.201 times s is 1.29 over the square root of 12. So that'll calculate our error. Once we have our error, we plug it into our interval formula, which is that the mean is between x bar minus e and x bar plus e, x bar being 8.98. So let's calculate our error. So I'll get 0.820. So then we plug it in here, we're going to get 8.98 minus 0.820. That's on the lower end. On the upper end, we have 8.98 plus 0.820. That's the upper end. So our mean should be between, the lower end ends up being 8.16, and the upper end is 9.8. So what does this mean? This means that we can estimate that the population of all people, okay, when they're hypnotized, this is about hypnotherapy, would on average sleep somewhere between 8.16 hours and 9.8 hours. Okay? Again, population estimate. Our sample mean was 8.98. Is that exactly the same as the population? No, but that's a basis for us creating this interval. And with this error, we said, well, it should be somewhere between these values. And we are 95% confident that that will be correct. There's a 95% probability that the mean is actually between these two values. All right, so here's another one. A random sample of statistics students were asked to estimate the total number of hours they spend watching television in an average week. So the responses are recorded, and these are the number of hours that was recorded. So here they give you all the data that you need. Okay, so we're going to use this sample data to construct a 98% confidence interval estimate for the mean number of hours statistics students will spend watching television. So for the whole population, all right, we looked at one class and asked them how many hours they spend. And so we're going to look at it now for a whole population and estimate it. So a couple of key things here. One, we need to figure out what the sample size is. Okay, n. So how many values do we have here in the table? So 1, 2, 3, 4, 5 by 3, so we got 15. Okay, so we have 15 values here. All right, what's the sample mean? Well, we would actually have to calculate that. I'd have to add all these up and divide by 15, in which case, if I actually did that, I would get 6.133. I already calculated this ahead of time to make this go a little faster, but you could calculate this on your own. We also need the sample standard deviation. Now, that's going to take us a little bit longer, but since we have all the data values and we knew what the mean was by calculating it, we could also use what we learned earlier in the semester to calculate the sample standard deviation. In which case, I already did this earlier, and I got 5.514. So that's the sample standard deviation. So the average number of hours, this is in hours, yes, the average number of hours, our sample of 15 students watched TV per week was about 6.133 with a standard deviation of about 5.514. All right, what else do we need here? Well, we need to do this with t-scores because we're talking about mean. And that's going to be a key you're going to have to remember here, is whether I should use t-scores or z-scores. So since we're doing it as it relates to mean and we're trying to do a confidence interval for mean, that right away tells me t-scores. All right, so we're going to use our confidence level of 98%, and we need 98%, and we need to use that to find our t alpha half. Okay. So what are we going to do? What we're going to do is we're going to draw our t distribution, which looks a lot like our z distribution. Our 98% is going to go in the middle. 98%, I did that again. 98% is going to go in the middle. The tails combined are 2%. So two tails, we have an area of 0.02. Or if you just looked at one of the tails, which would be 1%, that would be an area of 0.01. And we need to figure out what this t-score is, okay, this t alpha half. Well, we need one more thing here, and that's degrees of freedom. If our sample size is n, our degrees of freedom is going to be 14. So we have this degrees of freedom, we have this area in one tail or two tails, however you want to look at it, And then we can use our table to find our T alpha half. So here's our table. So our area in 2 tails was 2%, or our area in 1 tail is 1%. Either way, we're talking about this column here. Our degrees of freedom was 14, so our T alpha half is going to be this value right here. So our T alpha half, our T score, is going to be 2.624. Now, we take that and we use that for our margin of error formula. Margin of error formula says we take T alpha half times S over the square root of N. So using all the values we have already calculated, 2.624 times S, which was 5.514, that's kind of messy, 5.514 over the square root of the sample size. The sample size, remember, was 15. Plug that into our calculator, and we'll get our error. So I came up with a number of 3.736. All right. So once we have our error, and if you remember, our mean from our sample was 6.133, we can create our confidence interval. Remember, we're estimating the mean of the population, the average number of hours all statistics students watch TV in the course of a week. This was our sample value. And we're going to say, well, that's probably pretty close to the population value, about 6 hours. But it's not completely accurate. So what we're going to use is our sample value and our error to create our interval. So we estimate the mean of the population by doing the sample mean minus the error and the sample mean plus the error. And that gives us our interval for the mean of the population. Well, our sample mean was 6.133 minus our error, which was 3.736, and then we do 6.133 plus 3.736. And so then our interval for our mean of our population is between 2.397 on the lower end, okay, and on the upper end, 9.869. So the average number of hours the whole population will watch TV, a population of statistics students, let's say, will watch TV per week is somewhere between 2.397 hours and 9.869 hours. And we are 98% confident that that's going to contain our true population mean. There's a 98% chance that our population mean is actually somewhere in that range. Now, that's a pretty big range, but, you know, that's the value we got. So think to yourself, you're a statistics student. What's the average number of hours per week you watch TV? Is it somewhere between 2.397 and 9.869? I don't know. I think for me it might be a little more than that, but nonetheless, this is what we're doing. We're estimating the mean of the population using the mean of the sample. But when we do this, because of our sample sizes, because we're working with mean, we have to use t-scores. But other than that, the step process, the things we're trying to do are very similar to what we were doing with proportion in the previous lesson.